Hello and welcome to our lesson on simplifying radical expressions. This is going to be from section 6.3 in our text. Let's get started. So first of all, simplifying radical expressions means that you need to reduce your radicals to lowest terms. And we'll start with an easy example first. Number one, let's say we have the square root of 24. And we want to simplify completely. Well, the first thing you need to ask yourself is it already simplified completely? Or can I break down the 24 into factors where one of them is square rootable? And I'm not sure that's a word, but it sounds good. So here's what I'm talking about. We want numbers that multiply to make 24, one of which is a perfect square. And the reason we want it to be a perfect square, if you remember, the index is understood to be 2 when it's not there, and that implies that you need perfect squares. So 24, we know that 1 times 24 is 24. 1 will square root, but that'll leave me the square root of 24, so I haven't really made any progress. 2 times 12 is 24, but neither 2 or 12 are perfect squares, and so we keep looking. 3 times 8 is 24. 8 is a perfect cube, but we need a perfect square. So neither one of these are squares, and so we keep going, and eventually you'll arrive at 4 times 6. So 4 is a perfect square. And we want numbers that multiply to make 24 because there is a property of radicals that says if you have factors under a radical, you can separate them into their own houses. In other words, you can take the square root of each factor separately. So notice what I've done here is I've broken off a piece that I can simplify. The square root of 4 is 2. Notice it's not under the radical anymore because I took the square root of it. And 6 is going to remain under the square root because 6 is not a perfect square. 6 cannot break down. Now, if you think, is this simplified completely? You need to ask yourself, are there factors of 6 where one of them is a perfect square? And remember, 1 times 6 doesn't count. Even though 1 is a perfect square, you're still going to have the square root of 6, and so you haven't really made any progress. So the only other factors that multiply to make 6 are 2 and 3. Neither one of those are perfect squares, and so that means that this is simplified completely. So do you understand the objective here? The objective is to take what's under the radical. If it's a square root, you want a perfect square factor. And that then can simplify by taking the square root. Next example, number 9, we're going to look at the cube root of 54x to the 8th. Notice my index this time is a 3, and so we're looking for factors of 54, one of which is a perfect cube. And then for the x, there's a long way and a shortcut to simplify that. And so I think what I'll do is I'll show you the long way and then the shortcut. So you get both scenarios there. So for the 54 first, we're going to have the cube root of numbers that multiply to make 54. I happen to know 6 times 9 is 54. 9 is a perfect square, but I need a perfect cube. And so 6, I know 6 is 3 times 2, and 9 is 3 times 3. So if you look at what I've got here, I've got 3 factors of 3, which means that I want 27 and 2. So 27 times 2 makes 54, and 27 is a perfect cube. 3 times 3 times 3. Now for the x, x to the 8th, remember I said I'm going to show you the long way first. What you can do is you can write down 8 factors of x. This is definitely not efficient, especially if this exponent is big. But for 8, I can show you, well, kind of how it works without too much trouble here. So what you want to do for the variables, since our index is 3, is you want to take groups of 3 until you run out of groups of 3. Each group of 3 counts as one x that you can take out. So then to break this down, we can do the cube root of 27, which is 3, and I had 2 groups of x's, 2 groups of 3, so that means that I can bring out 2 x's. X times x brings out x squared. And then, for the rest of the radical, I'm going to look at what's left over. So I have a 2 left over and 2 x's. So the remaining part of the answer is going to have a 2 and an x squared as the radicand, the stuff under the radical. And this would be simplified completely. All right, so for our next example, I'm going to do number 9 again, but this time I'm going to take a different approach and show you how we can get to the answer a little bit faster. And this also is going to include a technique for people that have a hard time coming up with perfect squares or perfect cubes for your factors. So the first thing I want to do for my 54 is I want to find the prime factorization. To find the prime factorization of a number, you're going to start with the smallest prime number, which is 2. If it goes into 54, we're going to divide it, and we're going to keep using 2 until it doesn't work anymore. So 2 goes into 54 27 times, and then notice 2 is not going to work again. 2 doesn't go into 27, so we move to the next prime number, which is 3. 3 goes into 27 9 times. 3 is going to work again. 3 goes into 9 3 times, and 3 will work again. 3 goes into 3 1 time. So this is how you find the prime factorization of a number, starting with 2 and then using the prime numbers that'll divide into whatever's left until you get down to 1. The numbers out to the side are the prime factorization. We can express that as 2 times 3 cubed. Since there's 3 factors of 3, we can express that as 3 to the 3rd. Now, x to the 8th, we're just going to leave that x to the 8th for a second, and I'm going to show you how easy it is to simplify your variables. Okay, so what you want to do is you want to take the index and divide it into any exponents you have. Since the index doesn't go into the exponent for the factor of 2, 3 doesn't go into 1 evenly, the 2 is going to stay under the radical. Moving to the 3, the index divided into the exponent, 3 goes into 3 1 time, and that means that you can bring out a 3. In fact, all of the 3's come out because 3 goes into 3 evenly. And then for the x's, what you want to do is take the exponent divided by the index. 3 goes into 8 2 times. 2 times 3 is 6. Remainder of 2. So the quotient is how many x's get to come out, and the remainder is how many x's are left over. And that's how you can simplify those variables super easy. If we compare that to our previous answer, bam, you're going to see that we got the same answer. So there's 2 different approaches for how to simplify radical expressions. Next example, number 39. Here we're looking at multiplication of radical expressions. Probably the main thing you need to know is that in order to multiply radicals, they have to have the same index. So since both of these are square roots, they both have an index of 2. The first thing that I'm going to do is write a single radical expression, one single square root symbol, and we're going to multiply the radicands together. 8 times 12, 96. I do have a's under both radicals. Remember, when you multiply variables, you add their powers. So that's going to give me a to the 7th. We also have b's. B to the 1 times b squared gives me a b to the 3rd. Then you can take that result and make sure that it's in simplest radical form. Remember, the index is 2 for a square root. And so for the 96, you can either break it down into factors where one of the factors is a perfect square, or you can find the prime factorization. So what I'm going to do is I'm going to come over here to my 12 and 8, and I'm going to see if I can do it a little bit faster than doing prime factorization. I know that 12 is 4 times 3, and 4 is a perfect square. I know that 8 is 4 times 2, and there's another perfect square. So these, 4 times 4, that means that 16 is a factor of 96, and the other two factors are the other factor. 3 times 2 is 6. So 16 times 6 is 96, and what I've done here is I've got the largest perfect square that I can take out of 96. For the variables, we're going to divide. All right, so here we go. Final answer, taking the square root of 16 gives me a 4, and the 6 is going to be left under the radical. Then for the a's, we're going to do 7 divided by 2. 2 goes into 7 3 times with the remainder of 1. So that means that I can bring out 3 a's. Remember, the quotient is how many you bring out. The remainder is how many are left over. There's going to be 1 a left over. And then for the b, we're going to divide the exponent by the index. 2 goes into 3 one time with the remainder of 1. So I can bring out a b, and I'm going to be left with a b. How freaking easy. And that is simplified completely. Next example, number 65. Here we have a fraction with radicals top and bottom, and we need to perform the indicated operation, which is division. Now, if your radicals have the same index and the radicands will reduce, you can go ahead and reduce those. There is a property of radicals that says if you have a radical top and bottom and the indexes match, what you can do is you can make that one single radical expression and reduce your fraction. So we're going to reduce 48 over 3, x to the 9th over x, and y to the 13th over y to the 5th. And since every part of the denominator is smaller than the numerator, we are not going to have a fraction left over. Here we go. How many times does 3 go into 48? I believe that is 16. And then which has more x's, the top or the bottom? Well, the top does. How many more does he have? 9 is 8 more than 1. And so we're going to have x to the 8th left over. In other words, when you have x's top and bottom, you subtract their powers. And the x's in the denominator are gone because they all canceled out with the x's in the numerator. Finally, y to the 13th minus 5. 13 minus 5 is 8. Now, that is the first step of simplification. The next thing we need to do is make sure that the radicand is simplified completely. And our index is 4, which means we need a perfect whatever to the 4th power. 16 happens to be 2 to the 4th. 2 times 2 times 2 times 2 makes 16. So we can express 16 as 2 to the 4th, or you can simply say the 4th root of 16 is 2. Then for the variables, you're going to divide 8 divided by 4 twice. And those divide evenly. So that means I'm going to have a remainder of 0, which means I'm going to have no variables left under the radical. So 8 divided by 4 is 2. I'm going to have an x squared, y squared, and that is simplified completely. And our last example in this lesson, number 91, here we need to simplify the radical expression. We have a fraction under a 5th root. Again, we have a property of radicals that says if I've got a single radical over a fraction, I can separate it so that the numerator and the denominator both have the radical symbol. And the reason I'm going to go backwards this time, or it may appear that I'm going backwards and separating it, is because I noticed that the numerator and the denominator can simplify separately. So in the numerator, we need the 5th root of 32. Does 32 have a 5th root, or do I need to break it down? Well, we're going to practice the prime factorization one more time just to show you how easy that makes the process. When you're not sure what to do, at least you have a starting point there. Remember, the smallest prime number is 2. 2 goes into 32 16 times, and we're going to continue to divide by 2 until 2 doesn't work anymore. 2 goes into 16 8 times. 2 goes into 8 4 times. 2 goes into 4 2 times. And remember, you keep going until you get down to 1. And look at that. 1, 2, 3, 4, 5 2s. So that means that 32 is 2 to the 5th. And since the index and the exponent match, they'll cancel and leave me a 2. Or you could say the 5th root of 32 is 2 because 5 factors of 2 make 32. Now for the x, remember we're going to divide. You divide by the index. 8 does not divide by 5 evenly. So we're going to have some x's left under the radical. How many times does 5 go into 8? Well, it goes 1 time. So we can bring out 1x, and then the remainder is 3. I'll show that. 8 divided by 5. 1 times 5 is 5. 6, 7, 8. Remainder of 3 means that we're going to have 3 x's left over. X to the 3rd left under the radical. The quotient is the exponent outside, and you don't have to write an exponent of 1. The remainder is the exponent inside. And last, for the denominator, 10 divided by 5 is 2. And so that is going to simplify completely with no radical left in the denominator. And that is simplified completely. And that's going to do it for this particular lesson. So if you have any questions or comments about anything that I've done so far, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.